Where did everything come from? This is perhaps the biggest mystery that science has been striving to answer for decades, if not centuries. The question of how the universe came to be. Mankind's most curious minds have been yearning to figure out what is exactly that keeps the universe going and what is behind the creation of potentially infinite number of planets and clusters of stars residing in all the galaxies in the universe. Over the years, various theories have been presented by men and women of science that seek to explain what is it that governs all forms of matter and energy and why these things behave the way they do. With so many of these postulations, it has become a major objective of the scientific field of physics to perhaps combine all existing theories and laws about the universe and unify them into a single cohesive theory of everything. And one of the essential requirements involved in accomplishing this difficult objective is the discovery of the so-called God particle, which is what we're going to talk about today in this video. I'll start with this. For around the latter half of the 19th century and at the beginning of the new millennium, particle physics is largely governed by what is referred to as the Standard Model of physics. The Standard Model in particle physics is, for the moment, the most widely accepted theory that provides a decent explanation concerning the behavior of all forms of matter and energy in the universe, particularly the interaction of fundamental particles with elementary forces that exist in nature. According to the Standard Model, there are two types of fundamental particles: fermions, which are what matter is composed of, and bosons, which carry forces. These particles are identified and ordered in terms of several properties, specifically mass. The mystery surrounding these particles is that while their mass can be measured, scientists cannot say for certain where exactly their mass originated from and why they have such masses in the first place. So what explains the fact that these elementary particles actually have mass? Well, that's where the Higgs field comes in. In terms of the Standard Model, the Higgs field is known as a hypothetical force field which cannot be seen, but is said to exist in every area of the entire universe. It is also this field that gives mass to various elementary particles like quarks and electrons. A particle's interaction with the Higgs field when passing through it is theorized to be the one that gives the particle its mass. And the more that particle interacts with the invisible field, the more mass it contains. And so, according to this theory, without the Higgs field, nothing would exist the way that they do now. Not humans, not Earth, not the stars, and not the many galaxies in the universe. But how do we know the Higgs field actually exists? Well, many particle physicists believe that among the final missing pieces that could complete the puzzle, the God particle, one of the universe's force particles, will be the one to prove the field's existence and consequently provide a better understanding of the current Standard Model. So what exactly is the God particle? The term God particle was coined around the 1990s by Leon Lederman, a physicist and Nobel laureate who published a book about particle physics and discussed science's pursuit to discover a specific elementary particle referred to as the Higgs boson. Actually, many scientists dislike the title of God particle and would prefer to use the official term Higgs boson. But again, what is it exactly and why is it so important in proving the existence of Higgs field and evaluating the Standard Model? Well, the God particle, or the Higgs boson, was proposed by Peter Higgs around the 1960s as a necessary element to support the possibility of an invisible field permeating the universe. And to many particle physicists that agree with Higgs, the hypothetical existence of Higgs field requires science to also recognize the presence of the Higgs boson. Okay, that might sound really confusing, but here's an example. Picture a ball floating in a swimming pool. The ball is a particle while the pool is the Higgs field. The water of the pool is the one that gives the ball its mass. And if you excite the water by dropping a ball into the pool, it would of course cause a splash. According to quantum mechanics, this splash is the Higgs boson. And essentially, this God particle is an excitation of the invisible Higgs field. This means the key to validating the existence of the Higgs field lies in finding the Higgs boson, which some physicists believe could somehow be detected through the use of highly sophisticated scientific equipment. Now, theoretically, particle physicists had predicted that recording the existence of the Higgs boson cannot be accomplished by man-made instruments as the particle is too fleeting. And so one option they came up with that could confirm the creation of a God particle is by identifying and studying the particles it decays into. So this next to impossible search for the Higgs boson became among the main motivations in the $10 billion construction of the Large Hadron Collider by the European Organization for Nuclear Research, or CERN. The Large Hadron Collider, or LHC, is essentially an oval tunnel that stretches 17 miles under the border of Switzerland and France. It acts like a racetrack for when particles of matter are smashed together. This is made possible by the fact that surrounding its tunnel is around 9,000 superconducting magnets. These magnets accelerate the abundant stream of photons which travel inside the LHC in both directions, almost to the speed of light. At this speed, the photons travel through the tunnel around around 11,000 times per second. These photons can be directed to collide with each other for millions of times in only a blink of an eye. Sparks and particles are produced by these collisions as a result, and the debris of these particles are the ones captured, recorded, and analyzed by the scientists' high-powered computers. Among these particles, scientists hope to detect even the most minuscule droplet of the Higgs boson particle. But because the particle is anticipated to be unstable, they estimated that it would take a fraction of a second before the God particle disintegrated into other particles. And it is in these other particles that scientists hope to find a pattern of decay that could potentially be the fingerprint of the Higgs boson. So collecting data using the Large Hadron Collider officially began in early 2010, with ATLAS and CMS, two of the main teams in particle detection at LHC, tasked to pinpoint with accuracy and precision the mass range where the Higgs boson could exist. The two teams worked independently from each other, refraining from discussing their work outside of their respective groups. It was only around the end of 2011 that the two team leaders met with the Director General of CERN. It was then revealed that each team held suspicions that they may have finally found the Higgs boson, having narrowed down its mass at around 120 GeV. By July 2012, CERN announced that the ATLAS and CMS experiments at the Large Hadron Collider resulted to the discovery of a new boson particle with a mass range of 125 and 126 GeV. Both independent experiments reached a logical significance of 5 sigma, the conventional standard observed in particle physics before a discovery is officially declared. This meant that there was only one chance out of 3.5 million that each of the discoveries of the ATLAS and CMS teams were nothing more than a random fluctuation. It would take months of further studies before CERN would confirm with some degree of confidence that the new particle they discovered could potentially be the Higgs boson, which they did so in March of 2013. By October of that same year, Peter Higgs and Francois Englert were awarded the Nobel Prize in Physics for coming up with a theory that led to the discovery of a new fundamental particle and furthering the current understanding on subatomic particles and their mass. With all that said, considering the amazing scientific breakthrough achieved by scientists using the LHC, can we now say for absolute certainty that the discovery made at CERN was actually the Higgs boson? Well, at this point, men and women of science are refraining from positively saying so, because the truth of the matter is our ability to understand the universe is still very much limited, and nobody really wants to jump to conclusions. But after several tests following its discovery, the boson particle detected using the LHC remains until now consistent with the predictions of the standard model of particle physics. But whether it is actually the much sought after God particle, more data is required to conclude as such. And even if we have found it, the discovery of the so-called God particle would just really be the beginning of mankind's pursuit to understanding the origin of everything, which honestly I don't know if we will ever do, and I'm sort of okay with that. I'm okay with not knowing everything in life. I'm okay with having questions and having the mystery of life be there. But let me know what you guys think. Thank you all so much for watching this video. I'll see you later.